notes 12.1 part 2. Reversible reactions will often look like, not often, they always look more or less like this. And, well, actually, let me do this. Hold on 1 second. Alright. They look like this right here. There's a double arrow of some sort. Okay? You'll have a certain number of moles of A, reactant A, plus reactant B, a certain number of moles. And these italicized A and B's here, this lowercase, represent your coefficients in this case. And then you have coefficient C for product C and coefficient D for product D. Okay, so because these two things are never fully used up, and these are never fully created, the way that you figure out how much of these are made is by looking at a ratio. You can look at a ratio, and how you do that is you take it. The ratio is called the KEQ. And what the KEQ is, it's the concentration of products, that's this, over the concentration of reactants. Okay, and you can calculate the ratio of products to reactants and figure out, yeah, there's going to be mostly products made in this equilibrium, or there's not going to be a whole lot of product made. It's going to be mostly reactants left over. Okay, so here's how you calculate that. Again, this is your formula, concentration of products, and the brackets here mean concentration. Okay, brackets mean concentration of. Here, let's just say this so we don't forget. Brackets mean concentration of. Okay, that's what brackets mean. So let's go ahead and show you how to calculate these. It'll look like this. Your concentration of product C. Now you look at your coefficient C and you put it there as an exponent, times your concentration of product D. You look at your coefficient there, you put it to the D power, over your concentration of product A to the A power, times your concentration of product, reactant A to the A power, and reactant B to the B power. Okay, this applies, these equilibrium constants only apply at specific temperatures. Okay, so in the word problems it will say an equilibrium of this type of reaction takes place at equilibrium at 35 degrees Celsius. Okay, so in other words, the temperature has to be constant. Otherwise, if you fluctuate temperature, what's going to happen? Well, the equilibrium could get thrown out of balance. Okay, so it has to be at a constant temperature. Only gases and dissolved substances are in the KEQ. I don't think we're going to look at gases, but I think we are going to look only at dissolved substances are in the KEQ expression, since their concentrations vary. There goes that light. Hold on. Okay, only gases and dissolved substances are included in the KEQ expression, since their concentrations vary in a reaction. Think about what that's saying now. Solids do not have different concentrations, do they? A solid is a solid. It's got a density, right? We know that the density of gold is what it is, and the density of copper is what it is, etc. What about liquids? Well, liquids are pure substances. They don't have concentrations. So if we know that we've got pure water has a density. We don't need to calculate a concentration. Okay, it's got a density of 1 gram per mil. And just like pure ethanol or pure methane or whatever it might be, okay, has a density. They are not included in the KEQ since their concentrations are relatively constant. So you include gases and aqueous. You do not include solids and liquids. The equilibrium, so the reason they're telling you this is because sometimes, although here's one example down here, okay, you're not going to include this solid in your KEQ expression when you write it. Okay, so you need to really pay attention to this. You're going to get a wrong answer if you don't understand this. When you're writing out these KEQ expressions, you do not include solids and liquids. You only include gases and aqueous. Okay, I would probably highlight that. It includes this right here. Do not include, maybe put that in red or box it or something, I don't know. Do not include solids and liquids. When you're learning this stuff, they put those in there to throw you off. The equilibrium expression KEQ describes the extent of the reaction. In other words, by extent, we mean how much product was made. To what extent did that reaction move towards the product direction? If the KEQ is greater than 1 at equilibrium, the reaction is product favored. And that should make sense. If you've got a big number divided by a little number, then you're going to have a number greater than 1, aren't you? Right? I'll say it again. Big number divided by a little number. Look, big number over little equals greater than 1. You guys ever think about that? What about if you had a little number divided by a big number? Well, it's going to be less than 1. If it's approximately 1 at equilibrium, then you have approximately equal reactants and products. Okay. Now if it's less than 1, that means you've got a little number divided by a big number. So what's the little number here? Your little number would be your products. That's your products. Okay, that's the concentration of that. Divided by a big number, which is your reactants. That means it's going to be reactant favored. Okay. That's a real important concept. It's pretty simple. Once you get it down, you're like, oh, well, this makes sense. It's real easy. When you're first learning, it might seem a little complicated, but it's not. This is just a ratio of the amount of products to the amount of reactants, and you have to keep that in mind. You have to keep telling yourself that over and over when you're calculating this stuff. Otherwise, you're going to forget what it is that you're doing. So let's go ahead and write the equilibrium expression for the following reactions. So we say for this one, KEQ equals your concentration of H plus times your concentration of Cn minus divided by your concentration, and they're all AQ, so divided by your concentration of HCN. Now, I said they're all AQ, so this is fine. We can include all of them. And now I'm going to look for coefficients. There are none, so the coefficient is all 1, so that is our equilibrium expression. Okay, second one. Let me look first. These are all gas. Okay, so we can write the KEQ as follows. KEQ, we're going to include all of them. Now notice, look, I've only got one product here on the right side of the arrow, so be careful. I write my concentration of NO2, and there is a coefficient. I'm going to write it to the second power. Now I write my reactants underneath. Your concentration of NO to the second power times your concentration of O2. That's the KEQ expression for this second reaction. And now let's do the last one. This was the one where I told you, hey, you need to make a note of this. I'm highlighting it. You guys are just learning this stuff, and even I sometimes still miss this. There's a solid there. Okay, so what do I do in this case? I leave it out. And I just write the following. I say the KEQ then equals your concentration of Al3 plus, in brackets now, times your concentration of OH minus. Notice I'm including the charges, and there's a coefficient of 3. So that's my KEQ for this. How am I going to use this? Well, it might say in your question, I have 3 molar concentration of this and 2 molar concentration of that. What's my KEQ going to be? Something like that. Is the reaction going to be product favored or reactant favored? Okay, so that concludes these notes. You're to do your equilibrium worksheet that goes along with these notes.